One major component of the entire innovation system is, of course, the expenditures on research and development. In the SAM presented later, this can appear either as an aggregate expenditure along the column labeled R&D or as a set of disaggregated expenditures. In the latter case, these may be specified according to productive activities, for example, construction, electrical equipment, and so on, or by institutions. For example, private R&D expenditures, government R&D expenditures, and so forth. It should be emphasized that the dynamic effects of R&D on the economy can be captured only in a series of such SAMs over time. This approach is still at the conceptual stage, but appears to be quite appealing. So how do we really use a limited number of SAM to get the results that we want? That is the problem I'm posing on this page, page 42. In the following model, the main purpose is to establish a multiplicity of equilibria when the innovation system exhibits a nonlinear relationship between parts of the socioeconomic system. Such a relationship may obtain simply because of the existence of increasing returns to scale in production. Other types of nonlinearities may also be present. So this is a new thing that, at least as far as I know, that was introduced at that point by me. And then after discussing a number of substantial issues on the next page, page 43, I turn to specifying the model. So I tell the reader here, we begin with a number of productive activities reflecting the existing technological structure. We also incorporate the possibility of R&D as a separate productive activity. At the level of abstraction at which we are working, it is always possible to break R&D down into as many finite components as we want. Later, I actually show these things. And I did it for both South Korea and for Taiwan in this particular book. But now we want to assume that we have some SAMs, and we want to create a nonlinear model that would have multiple equilibria. So we define, again, the entire economy as a vector of accounts, not just outputs. So here, to be consistent, I use the vector x as all the accounts. So that would correspond to the rows that we saw earlier for the Indonesian SAM, for example. And then to emphasize the nonlinear nature, we write n, which is not a matrix. A matrix is a linear transformation. So this is a non-linear relation. You can think of the elements of this thing, if you think of it as a matrix, elements of the matrix themselves would be nonlinear functions of various sorts. So it's kind of complicated. And then we have final demand. And I have proved results for two kinds of mathematical spaces. One space is called a vector lattice, and the others is called a Banach space. Somehow those pages did not come here, but I will simply point out what is at stake by drawing a diagram. A diagram is always simpler than the proofs. And maybe I will give you a sketch of the proof. But let's draw the diagram first. So here we have this x, and here we have the function nx plus d. And the function is nonlinear. So the problem is really one of computing fixed points, so that we have to find x star, so that x star equals nx star plus d. That is the problem to solve. And one simple way to do that is to just draw a 45-degree line. Oops. There. Let's assume it's a 45-degree line. Okay. Looks like it's close to it. And then the actual nonlinear function might look something like this. Okay. But it intersects this 45-degree line here at A, B, and C, and maybe in other places, but we don't need to go so far. And of course, the property of 45-degree line is that at each of those points of intersection, this equation would hold, right? X star would equal nx star plus d. So that is the graphical solution to this problem. But to solve this algebraically, mathematically, you have to compute these fixed points. And first of all, you have to show that fixed points exist. And I did that in two different spaces, as I said, first on vector lattice, where you have to define the order completeness of these. In other words, you really need to know that these things can be ranked in some way. In real number system, it's simple. We know what's bigger than what. But we are dealing with very complex multidimensional spaces. So defining what's bigger than what is a little more complicated. And then you have to be, you need a condition that at least one output is possible. And roughly under those conditions, which can be specified rigorously, and I have done so in my books and papers. If anybody is interested, I can give references. But I think it is sufficient to look at this picture and know that multiple equilibria are possible. And you can show that it would be under very restrictive conditions that the equilibrium would be unique. Now, multiple equilibria in this nonlinear model allow us to do something really beautiful, something very elegant in terms of the dynamics of innovation. A country like South Korea or Taiwan can start as being very poor. In fact, in the 1950s, they were the two poorest countries in the world. But gradually, they came up through a combination of policies and other opportunities. In some of those, they were just lucky. But others were policy maneuvers and strategies they followed. So today, both are fairly rich economies with quite amazingly sophisticated innovation systems. It's especially amazing for Taiwan, which is a smaller economy than Korean economy even. Taiwan actually has probably the highest proportion of PhDs as politicians. It's not that they couldn't find employment in their own fields. Most of them actually have PhDs in fields like philosophy and history, and they could have taught at Taiwanese universities. Many did, but they became very socially concerned after the democratization of Taiwan. And many of them are actually very good citizen politicians in Taiwan. They are much more interesting to talk to than politicians anywhere else in the world, in my experience. But this miracle, if you can call it a miracle, was possible because of this existence of multiple equilibria. Of course, the policymakers themselves did not act from a model like this, but they had some intuitions. The intuitions were that, well, you begin at a small or low equilibrium. Say you begin at point A. Then you move to point B, then you move to point C, and other points that are all higher. So you can have a sequential equilibria. And in a multiple equilibrium world, you may be able to choose close to the best possible equilibrium at one point in time. And then the next step would be to find the next best equilibrium, and so on and so forth. Deng Xiaoping may have had something similar in mind when he said that we have to just feel the next stone before we cross the river. We don't know how to cross the entire river at once. So something like this may have been at work in Taiwan, in South Korea. Today, of course, they are much more sophisticated and have tremendously sophisticated research apparatus in economics especially. Both Korea Development Institute and in Taipei, the National Research Institute, as well as several quasi-governmental and private research institutes have very good economists. And these people really are both incisive and precise theoretically, and also very practical when it comes to implementation of the policy. But most of all, they are very good at collecting information. And this is really the crucial thing. And we started with the collection of information, and we are coming back now to the collection of information. And I can simply finish by quoting Tinbergen. This is from his Nobel lecture And he says, this more fundamental research in economics deserves relatively more attention and resources than the more superficial versions of economic research directed at forecasting or analyzing very short-term fluctuations in market prices, or on which quite some money is being spent today. So I guess he was an understated Dutchman, but at the same time very direct. I cannot really overemphasize the importance of collecting good quality data and socioeconomic information. Much of the best work in America in the history of our discipline really has been done by people like Simon Kuznets and others, by people like Leontiev. Both of them won Nobel Prize, by the way, for their contributions. And these people knew that you have to have good data which can be made better if you have good theory also. And therefore the creation of good theory and good data, they really go hand in hand, they go together. But if you don't have a good theory, and most social sciences are not blessed with very good theories, you must absolutely focus on collecting the best data that you can and looking at data very, very carefully. And if there is to be a final word in econometrics, for me, that is the final word. We are all very clever. We can play with mathematical functions and create all kinds of models in our head and with pen and paper, but we should not confuse them with reality. They are fun to play with, and some of them might turn out to approximate reality well enough. But the only way we can find out is by collecting data and testing the theories in light of the data and specifying all kinds of causal paths and mechanisms. And that's why the structural path analysis that I showed you before is also very important. Okay, I think we are done.